Again, on behalf of AI for Industry Foundation, welcome to the first seminar of the Compagnia di San Paolo Institute of Advanced Studies. The audience will be international. There are a lot of people connected to the streaming, and this session will also be recorded and will be posted on YouTube. For this reason, we will have this session and the following sessions in English. Benvenuti al primo seminario dell'Istituto di Studi Avanzati della Compagnia di San Paolo. E, come stavo dicendo in inglese, l'audience è internazionale, abbiamo molte persone collegate in streaming e quindi da adesso in poi tutto sarà detto in inglese. Magari due parole sull'Istituto di Studi Avanzati. È una iniziativa congiunta di AI for Industry e della Compagnia di San Paolo che supporta pienamente e interamente l'iniziativa. It is a joint initiative of AI for Industry Foundation and the Compagnia di San Paolo Foundation, who supports the entire initiative. And to this regard, I would like to deeply thank Fondazione Compagnia di San Paolo for the huge support and collaboration so far. The Institute's objective is to foster the local AI ecosystem, connecting the best AI research worldwide with the innovation system locally and at the European level, including both scientists and decision makers. The Institute is a stream of seminars, events, wider policy papers that will unfold in the course of the next months and years. I wouldn't steal you more time than this. I would just like to pass the microphone to the chairman of the Foundation Compagnia di San Paolo, who would like to give a salute to all of you. Thank you, Mr. Gilli.
Thank you, and just really a few words. I'm very pleased to be here, and I'm very pleased that this is the first seminar of our joint collaboration with the Institute for Artificial Intelligence, the National Institute for AI here. As a Center of Advanced Studies, we hope to promote cooperation between this center that we expect to be a visible center hub of innovation in artificial intelligence and the best academic and industrial center all over the world. So it's really a pleasure to have today here Marco Pavone and Riccardo Mariani. When I was the director of the Technical University of Torino. By the way, I would like to welcome also the Deputy Rector, Elena Baralis, of the Politecnico di Torino. I met Marco in Stanford. At that time, he's still responsible for the center of the automotive center in Stanford. And from that point, we started a kind of collaboration together. So I'm very pleased that now he's a part of the advisory board of the Center AI for Industry, and also that now is here for the first seminar of this Center of Advanced Study. So thank you for all the audience, and if you agree, we can give the floor to Marco and to Riccardo.
Thank you very much, Mr. Gilli. So finally, before introducing our distinguished speaker, I would like to transmit the greetings of our chairman, Fabio Pamolli, who deeply believed and deeply wanted this initiative, the Institute of Advanced Study. He apologizes for not being here physically today because he's a commitment with the Ministry of Finance in preparation for the ECOFIN, so he had to make a choice. So again, thank you also to Mr. Pamolli for igniting this initiative as well. And then finally, let me introduce Professor Marco Pavone. He's Associate Professor of Aeronautics and Astronautics in University of Stanford. He's also Senior Director of Autonomous Vehicles Research at NVIDIA. So thank you very much for being here today, Professor Pavone.
Thank you very much for the kind invitation and the presentation and for coming here. And I'm honored to be the first speaker. As you could see in the previous slide, this is the seminar number 1 for the Institute of Advanced Studies. So it's a great honor to launch this initiative. So what I'll do today is to discuss some of my research towards leveraging foundation models, that is powerful AI models, to boost the performance of autonomous systems, and in particular, autonomous vehicle systems. Now, broadly, the goal of my research is to devise methodologies for the analysis, design, and control of autonomous systems. That is, robotic systems that must be purposefully react to situations that cannot be foreseen at the design stage. A key application domain of my work is space robotics. Indeed, before joining Stanford in 2012, I was a robotics engineer at the NASA Jet Propulsion Lab. And at the time, I was working on the decision-making algorithms for the entry, descent, and landing phase of Mars missions, which is only a 7-minute part of the mission, but very consequential mission, meaning that if you screw up, then you crash the spacecraft. And then since then, I've worked on a variety of different space robotics projects. For example, still at JPL, I was in charge of developing robotic platforms for the exploration of low-gravity bodies, such as asteroids and comets. On those planetary bodies, gravity is extremely low, so traditional mobility systems based on wheels do not work well anymore, because of course you will spin in place. So we devised a completely different mobility paradigm, whereby the idea is to spin internal wheels within the platform, with the idea that by first accelerating these internal wheels and then quickly decelerating them, we can transfer the angular momentum to the outside enclosure, and this gives rise to reaction forces from the soil that let the robot either hop or tumble or shuffle in place. So this is a very good design, terrible design for Earth. It's very energy inefficient. It wouldn't really work, but in very low gravity environments, where basically if I were to drop this laptop from here, it would take a couple of minutes to reach the surface, is a very advantageous concept. Of course, a key challenge to test these robotic systems is that on Earth, we have Earth gravity. So we devised a fairly innovative testing platform whereby we offload the gravity through a gantry that has a cable through which the robot is attached within a gimbal. So we remove almost all of the gravity, but not all of it. So we can really test the low gravity environments that you will find on an asteroid or comet. We're also working on some other crazy robotic concepts. So this is a concept whereby we leverage lightweight extendable booms to achieve a large reach with a small footprint. So the idea here is that if you have a robot, this is really tape measurement and stands out. So think about if you are a climber, what if you could extend your arm to increase your reach? So that's the idea of this robot. And the motivation behind this type of robot is to be able to explore very challenging environments, for example, on Mars. For example, exploring Mars caverns or rappel down cliffs on Mars to observe the strata. Other things we've been working on are grippers that use adhesive materials very similar to the ones found in the feet of the gecko, the lizards. And we manufactured them, we sent them to space, and we tested them on the International Space Station. And the idea is to have free-floating robotic platforms that can help astronauts with very boring but time-consuming tasks, like, for example, logistical tasks. It turns out that astronauts spend a lot of time to unpack cargo, move cargo from one point on the International Space Station to the other one. So there is a strong interest from NASA to have this type of small robots with adhesive capabilities to do the unpacking for the astronauts, so that the astronauts can, that of course cost a lot of money per hour, can focus on other more meaningful tasks. But my other key application domain, indeed the focus of this talk, is ground autonomous vehicles, and in particular self-driving cars. As Dr. Gilli mentioned before, at Stanford, I lead the Center for Automotive Research at Stanford, where we study a number of aspects related to autonomous driving, from motion planning algorithms to perception algorithms, behavior prediction algorithms, and so on. And I'm also fortunate to lead autonomous systems research at NVIDIA. NVIDIA has indeed one of the largest programs in the field of vehicle autonomy from the hardware all the way to the cloud. So it's a nice complement to my academic type of research. So given this introduction, the premise of this talk is that foundation models provide the key opportunities to dramatically accelerate the development of autonomous systems and the physical AI systems. With physical AI systems, we mean AI systems with a physical embodiment, so an AI that you can touch, like, for example, a robotic system and so on. Now, to be more specific here, by foundation model, I mean a model that is trained on broad data, typically at internet scale and in a self-supervised fashion, and that can then be fine-tuned to many different downstream tasks. Example of foundation models include large language models, ChatGPT, just to be clear, vision language models, video generation models, and more. An example of foundation models can be found at this link that I provided here, where NVIDIA has a catalog of ready-to-be-used foundation models that you can play with. So if you're interested, I would suggest you to just play with them, just to get an appreciation of the capabilities. Now, we are not quite yet at the level of one massive model that can ingest any data modality. It can then be adapted to any possible downstream use case. But this idea of pre-training on very large data, I mean, literally internet-scale data, and then fine-tuning to downstream tasks has proven useful in a variety of different domains. So then, it's tempting to say that AI makes everything better, so let's apply it to autonomous vehicles as well. Well, before applying foundation models to autonomous vehicles, it's important to contextualize in what ways foundation models can boost the performance and safety of AVs, of autonomous vehicles. And indeed, the AV technology, the autonomous vehicle technology, is already quite reliable in specific operational design domains, with advanced driver assistance systems being productized as we speak, and full-scale, completely autonomous robotaxis providing service without any safety driver, for example, in the city of San Francisco, in many other cities in the United States. And so far, this has been powered by the judicious incorporation of specialist machine learning models into the driving stack, like, for example, deep learning for perception or deep learning for behavior prediction and so on and so forth. However, these systems still miss the mark on the long tail of events that you could encounter as you drive around. So, for example, here I'm showing some difficult conditions that might still create significant challenges for a modern AV stack, including adverse weather conditions. So here is an interesting one. Is there a laser pointer? Maybe? No. Anyway, so here you can see traffic lights on a truck that can be interpreted as legal traffic lights. We'll come back later to this example. Or on the bottom right, I don't even know what that is. It's sort of a giant inflatable mignon in the middle of a road. And somehow the vehicle has to interpret that probably an inflatable object is not a cause of concern, so maybe you could push it out of the way. So at this point, it's useful to consider how humans, we, navigated the long tail of events. Well, as humans, we bring in a lifetime of general experiences beyond driving to the task of driving. And this generalist experience provides us with strong contextual and semantic understanding of a scene, which allow us to typically reason well in corner cases. Well, analogously, the hypothesis is that the foundation models that have been trained on multiple lifetimes of very diverse data, both from the driving domain, but crucially also from the non-driving domain, allow us to bring this generalist experience to the task of driving. At least this is the hypothesis. Now, the question is, how can we access this generalist experience for AV applications? And the answer is in multiple ways. As I'll discuss in the rest of this talk, foundation models can empower several different aspects of AV design, from offline development processes, for example, simulation, auto-labeling of data, scenario generation, all the way to the onboard stack, either by enabling new designs or improving existing designs. So the bottom line here is that the foundation models provide opportunities to accelerate the full development life cycle of an autonomous system, so a physical AI system broadly. Of course, safety is paramount. Here, we're fortunate to also have Dr. Riccardo Mariani, who is the VP of Safety at NVIDIA. And a common concern is that foundation models might not be safely fielded in a safety-critical application such as autonomous driving. Well, as I'll discuss later in the presentation, we do have a lot of tools to keep the AI in check, but also, and this is something that sometimes is overlooked, this powerful AI, so foundation models can provide opportunities to make autonomous systems safer, for example, with more sophisticated runtime monitors. So what I'll do in the rest of this presentation is to provide examples in terms of how we are applying foundation models throughout the development lifecycle, from offline development processes, particularly simulation, all the way to the onboard stack. And then I will conclude with some consideration related to safely fielding foundation models. Of course, feel free to stop me anytime if you have questions. All right, let me start by discussing how foundation models can significantly advance offline development processes, and in particular, the state-of-the-art in AV simulation. Now, in the past few years, neural field representations such as NeRFs or Gaussian plotting have emerged as an extremely powerful tool for scene representation and reconstruction. As shown in this video, our recent work, MRNeRF, can decompose a complex scene into its constituent static, dynamic, as well as estimated scene flow, thereby providing scene reconstruction and representation in 4D. So this is an AI model that can seamlessly deconstruct the scene, understanding what are the dynamic objects, what are the static elements, and so on and so forth. And importantly, all of this is achieved solely through self-supervision. So the AI learns to do this without relying on any external labels provided by humans. The reason why this is important is that with such a scene representation tool that is geometrically accurate, one can now simulate sensor data in a highly realistic fashion, such as in these resimulated multi-view videos capturing novel unseen viewpoints. So this is the video taken from a fleet car. So this is a real video. So this is a reconstructed video of the same scene, but viewed from different viewpoints. And probably you can tell that this is AI generated, and this is actually a real video. So this shows that actually now we have simulation capabilities that dramatically close the scene to real gap from at least a visual standpoint. And of course, you're not limited to regenerate camera data. You can also generate, for example, point cloud, so LiDAR data, which is one of the other popular sensors that you will have on a vehicle. Now, a caveat is that in all of these videos, the dynamic elements of a scene, like for example, pedestrians, bikers, and cars, are being replayed. So they do not really react to what the autonomous vehicle is doing. And of course, to fully close the loop on a simulation, we want to also build behavioral models that model how, for example, a biker would react to an autonomous car. Bikers, by the way, are the worst. I mean, I'm a biker, but the bikers are the worst from a simulation standpoint because they are essentially as dynamic as a car, but as erratic as a pedestrian. So this requires a lot of careful modeling. So accordingly, in my group, we have also conducted a lot of research in traffic simulation, pushing the state of the art in terms of realism, diversity, and controllability. So these are essentially data-driven models that learn from expert data, so from observations, how humans will react in different situations. And our latest model, which is called CAT-K, is a model that now has topped the leaderboard in terms of behavioral models. Now, while this is great, so now we have a technology to dramatically close the gap from a visual realism standpoint, as I showed you before, and also close the gap from a behavioral realism standpoint. I really didn't show you any specific results. I just made a statement there. There is still a caveat that generating scenarios that stress test an autonomous vehicle to really test whether the autonomous vehicle would do reasonable things in difficult scenarios is difficult. So typically you need designers and engineers that carefully craft a possible scenario with respect to which you want to test the vehicle. Well, this is a setting where foundation models can boost our existing capabilities. Specifically, we have explored how large language models can enable a new and intuitive interface to controlling the generation of simulation scenarios. With our recent work, which is called LCT Gen, we're able to not only control the initialization, but also an evolution of a scene by just using text prompt. So I refer to it as generative AI on steroids. It's not text to image, it's not text to video, it's really text to closed loop simulation. The way that this system works, briefly, is by first converting a given scenario prompt. Like, for example, I want to generate a scenario where some driver is drunk or inattentive, where we translate that given scenario prompt into a structured representation that is taken as an input to a map generation framework that essentially instantiates a map that is most aligned with the structural representation. And that structural representation is also taken as an input to a motion generation that instantiates the decision-making policies for all the other actors in the scene. The interesting thing about all of this is that you can condition the generation of the scenarios on any source of text data. In particular, what we did was to mine the full data set of crash reports that have been collected by the police in the United States in the past few years. This is a data set that has been put together by NHTSA, the National Highway Administration in the United States. And here there are some excerpts of the police reports of accidents that have actually happened. And you know, police reports are just very sparse scripts. So we use this kind of generative AI capabilities to complement them in a way that is plausible. So why this is important is that generating scenarios that stress test a vehicle, challenge a vehicle, is relatively easy. Generating a scenario that stress tests a vehicle and is also plausible, meaning it's not excessively adversarial, that's the tricky part. So here we're basically imbuing plausibility in the generation process by grounding the generation process into scenarios that have actually happened. And so putting everything together, we can combine scene reconstruction pipelines with the capability of generating targeted scenarios via language guidance to simultaneously simulate sensor and human agent behaviors in novel targeted ways. So here in this example, we have on the top row, a video that has been taken by a fleet car. So this is a real vehicle that has been recorded somewhere in San Francisco. And here, there's a car that is approaching from the left, and is stopping at the stop sign. And now, as a safety engineer, what I want to do is, okay, so give me a scenario that is similar to this one. I mean, this comes from the real world, so it's plausible. But now change it so that you make the behavior of that vehicle erratic, whereby the driver is inattentive. So all these models in concert, what they do is to take that car, this car here, remove it from the scene, put it back into the scene, and make it, fly through the intersection without paying attention to the stop sign. And this is completely AI generated. So this is a scenario that never existed. So this is the output of the pipeline. So this is the type of technology that now we have, for example, to stress test autonomous vehicles. But of course, you can also use these technologies for in a manipulation setting or in other robotics settings. So any questions here? Okay. So this is exciting, but there is still a fundamental caveat. So there are a lot of caveats when you develop autonomous systems. Yes?
Since you asked, One technical question is, you generate scenarios using what, stable diffusion or this kind of, so together with language models. That's
right. Yeah. So
that
basically, we use a diffusion model with I mean, we had different variants, but one of the systems we use a diffusion model with language guidance, whereby in the denoising process, we guide the denoising process with an additional loss.
But more conceptually, I mean, here you're trying to generate all possible scenarios and learn from them.
Not all possible. So that's the catch. Because if you generate any possible scenario, you might also generate some that are so adversarial that will never happen.
My question is more about how do you represent uncertainty? I mean, is it more efficient to learn from an astronomical number of examples, or rather try to work more on representing uncertainty and learn slightly more abstract concepts? I mean,
yeah, I mean, that's one of the hottest, I would say, questions in the field of robotics. To what extent you rely on abstractions, keeping in mind that the abstractions per se would also be learned. So people think about concepts and so on and so forth. I would say that currently in the current state of robotics is still a little bit brute force. So what pretty much everybody does is behavioral cloning, where decision-making is represented at the level of a single trajectory, which is a bit brute forcing the problem. But now I think we're moving into a phase 2, where again, models and abstractions are coming back. So people are thinking about ways to represent the policy, decision-making policies in a more structured way. So for example, instead of outputting a trajectory, you insert an inductive bias that the policy should output a value function. And then what you do for decision-making, for example, is search through that value function. So putting back those kind of foundational insights from dynamic optimization, Bellman equations, and so on and so forth. But I would say state-of-the-art for now is still a bit brute forcing the problem. The idea is that, of course, by making the problem as free of constraints as possible, you can gracefully scale with data. But that also has pitfalls. So I do think that at the end of the day, that's also what we're working on. There will be a moment where we will come back to more abstract reasoning and potentially even symbolic reasoning back into the equation. Yeah.
Excuse me, just interrupting because we had the first question, just to let the people on streaming to know that they can book questions for the end of the sessions by clicking the hand symbol in the platform. And then the director will give you the microphone at the end of the session. Thank you for this.
Okay, so one caveat that I wanted to mention is that the tools that some of the tools I've shown before rely on neural reconstruction. So what these tools do, like for example, NERFs, is to reconstruct an environment. And so that allows essentially you to generate a new scene with the different viewpoints, maybe 10, 20 degrees, or with some displacement with respect to the position, with respect to which a video was recorded, maybe a couple of meters laterally or a couple of meters longitudinally. But then at some point, those reconstruction models break down. Just to show you an example. So here we are testing a vehicle into a reconstructed environment where now the vehicle makes a U-turn. The reconstruction was based on a drive that was straight. And you see that as the vehicle is making a U-turn, you see a lot of artifacts popping out into the scene with a mass of holes, like for example, these are not clouds, these are holes. It's the AI model that is breaking because you're doing a maneuver that is too different with respect to the one that was used to generate the scenario. And in any case, with the reconstruction scenarios, by definition, you reconstruct, so you can't really do something completely different with respect to what was observed in real life. So the question is, how do we go past that? How do we generate a completely new scenarios? Well, as you probably know, another type of foundation model that has been gaining a lot of popularity recently is represented by video generation models. So these are like, for example, Sora from OpenAI and others more recently. So these are models that generate videos instead of language. For example, here I'm showing you videos generated by a video generation model developed by NVIDIA. So all the vehicles that you see here, all the videos that you see here never existed. All the videos you see here never existed. They're all AI generated. So that looks pretty amazing, right? Personally, I wouldn't said this would have been possible even 3-4 years ago. But they're not perfect. So for example, look here what happens. So you have a motorbike that then disappears, right? So the model was not exposed to too many motorbikes, so you probably understand the physics of it. And then you have this kind of a weird artifacts. So basically these models have hallucinations. And it's a problem because then testing becomes invalid and training becomes invalid, let alone validation that becomes invalid. So then the question becomes how we can leverage the strong generalization capabilities of video generation models. We take into account the problem that might still hallucinate. Well, one of the things that you could do is to, of course, improve your video generation model, but that still will require quite a bit of time. There is quite a bit of work indeed in trying to, going back to the previous question, induce some inductive biases, for example, to enforce temporal consistency in the generation process. But another thing that you can do, and that what we've been exploring recently in the paper that we presented a couple of months ago, is to combine the best of both worlds from the field of neural representations and video generation. So basically the geometric accuracy of neural representations with the generalization capabilities of video generation models. So what we do is to take an initial image of a scene. For example, this is a scene from Japan, and then use it to condition the generation of a video with a video generation model. So this is a video that is generated from that initial scene. See how weirdly the color of the grass flickers between green and brown. This is, of course, a hallucination. The grass cannot change colors so quickly. But then we pass this video generation to 4D reconstruction pipeline, and that gives basically imbues the generation with the physical and geometric accuracy, and then we can drive into that reconstruction world. So basically bring together these two separate branches of AI research into one model, and this works pretty well. And now this was one of the first works that was trying to combine neural representations with video generation. Now this is something that is getting quite a bit of momentum. So I would say that simulation has always been the holy grail of robotics. Of course, if we had a perfect simulator, robotics development would be dramatically accelerated. But until, I would say, 2021, 2022, simulation was not used as much in a production context. It was typically used mostly in a log replay type of context. But now with all these technologies, simulation is becoming a really prominent tool for the design of autonomous systems, both from the point of view of testing, but also to generate new data, to train the model, and so on and so forth. Anyways, with that said, let's go one step further and see how foundation models can also provide key opportunities for direct use into an AV stack. As mentioned at the beginning, foundation models hold the promise of allow us to drive better through better generalization. But the question is, do we have evidence for that? I mean, it's suggestive, but do we have a scientific evidence for that? So we recently explored this question through a work which we call agent driver. I confirmed that there is potential. So what this work agent driver does is to treat large language models as embodied agents that call different functions or capabilities on demand by using language as a unified interface. So basically, the language model is exposed with the image of a scene, and then decides to say call an object detector to detect the different objects in the scene, maybe a motion predictor to understand what these objects will do in the future. And when the large language model thinks that it has enough information, that it decides to produce a trajectory, then the vehicle executes. Of course, this is not how you would architect an autonomous system. The latency of such a system will be terrible. I mean, probably you are familiar with ChatGPT, you know that it's pretty slow. But the point here was more to test the capabilities rather than the real-world implementability of the system. And interesting, these are the results that we found. So in this plot, on the x-axis, I show the percentage of AD-specific data that is used to train a model. And on the y-axis, I have two different KPIs or performance metrics that we use to judge a model. Specific numbers are not too important. And the line represents the value for the best state-of-the-art academic model. So we see that agent driver with only 1% of the V-specific data that was used to train the best performance academic model, it already improves the state of the art. And then as of course increases the amount of training data, the performance gets better and better. And the point is that there is no magic here. So what agent driver is doing is leveraging all the knowledge that it has acquired through internet scale pre-training to the task of driving, so as that it only needs a very little amount of driving data in order to already beat the state of the art. I mean, this is the reason why as humans, we only require, say, 1 week to learn to drive, because of course we have so many other experiences in our past lives that contributed to getting capable of driving. Okay, so it seems that there is potential in terms of using large language models or vision language model as part of an autonomy stack. So basically language generation correlates well, it seems, with the task of driving. So how do you actually field a large language model in an autonomy stack? So this leads to one of my favorite topics, that is that of system architecting. The design space is huge. There are many different ways you can architect an autonomy stack. And to reason about such a huge design space, in a paper that we presented last year at CVPR, we proposed a computational graph framework to model the general driving task. Through this framework, we can reason about different architectural choices, for example, in terms of which modules to use, how to arrange modules in terms of dependencies, and how information should be represented from latent features all the way to interpretable outputs. And I'm quite excited about this type of work, as it provides one of the first tools to systematically reason with respect to different architectural choices. As thanks to this framework, we were able to conduct extensive experiments, and the end result is interesting and somewhat surprising. So it turns out that one of the simplest design, namely a fully parallelized AV architecture, is the one that seems to perform better. Briefly, this architecture, which we call a paradrive, entails a transformer that takes multi-camera images as an input and produces outputs in parallel for 4 core AV tasks, namely mapping, motion prediction, occupancy prediction, and motion planning. So this architecture follows the paradigm of train heavy and infer light. So put a lot of compute on the training part, and then trying to be very lean when you do inference in real time for the vehicle. Specifically in offline training, all parallel heads are necessary and crucial, as the code training through these different tasks allow the models to build internal representations for different tasks that are useful for driving, thereby yielding strong planning performance. But at inference time, we only have to infer the motion planning head in order to come up with an action that then the vehicle executes, and then you move on. In head-to-end comparisons with the state-of-the-art models, we show that this model is actually safer in terms of reducing dramatically the number of undesired behavior, unsafe behaviors, and also more efficient. And interestingly, you can still infer through the other parallel heads, maybe at a lower frequency, to gain some introspection into what the model is doing, or for example, for cross-checking what the algorithmic stack is doing with some other signals in order to understand, for example, whether the AV stack is healthy and is not doing something crazy. So this type of architecture naturally leads to multiple timescale decision-making, which is a very important concept in the field of controls. So encouraged by these preliminary results, we further extended this archetype with 3 core lessons from the design of foundation models, namely the use of scalable self-supervised losses, namely next video and language token prediction, a tokens in, tokens out autoregressive transformer backbone, which itself could be trained from scratch or could be based on a pre-trained large language models or vision language model, and then the use of internet pre-trained foundation models for tokenization. And to evaluate this foundation model empowered design, we implemented a version of the model that uses a video generation as an auxiliary training loss and an autoregressive transformer that is trained from scratch. Of course, while we're driving, we're not generating videos. That would be completely useless. We only do that at training time to basically imbue the model with a strong representation of how the world works. So we tested this system in a photorealistic sensor simulator based on neural rendering that we have at NVIDIA. And we see that we can drive it pretty well in a number of different situations. And we can achieve all these behaviors with a fraction of time and cost that will be needed with a more classical stack. And after gaining confidence into the model, we tested on the road, actually close to NVIDIA headquarters, and the model was driving fine for several minutes without any intervention from a safety driver, demonstrating behaviors such as lane keeping, nudging, intersection negotiation, and so on and so forth. That was last year. So a model similar to this one is now being productized as part of the NVIDIA AV program. So we're talking about tech transfer. So that's the pace at which tech transfer happens. So this was like a research last year, is now part of the AV productization effort. So I had to move on as a researcher to something else. So that something else is to now, that's what we're working this year, is to see what are the potential for real of using internet pre-trained vision language model as part of the primary algorithmic backbone. So these are results that we achieved about 3 months ago, which compare two models. So x-axis is the number of epochs that are used to train the neural network. The y-axis is one of the performance metrics that we use to judge the quality of a model. Average displacement error here, but it's not too important. So we compare the performance of an AV stack, so a neural network, for AV driving that does not leverage large language model pre-training, and the one that leverages actually large language model pre-training. So here you see two things. First, large language model helps with converging faster, and it converges to a better steady state. And actually, this gap is quite significant. So we have currently conducted a closed loop evaluation of this large language pre-trained model as in our neurosimulator-based simulator, observing very good performance. So we're actually now hardening the model in a number of ways. So specifically, as I mentioned, it's quite evident that language capabilities improve performance. So what can we do next? Well, with those that are familiar with the control theory background, there are several desiderata that, again, goes back to your question. Several desiderata that now we would like to tackle as researchers. Like, for example, how do we include the constraints and guardrails in the generation process? Or how do we more explicitly account for uncertainty? Most of the models out there don't really explicit reason about uncertainty yet. How do we imbue notions of a Bibo-like stability so that basically your system doesn't go crazy? And how do we more explicitly account for closed loop performance requirements? So fortunately, there are several directions that are ripe for investigation to collectively address these goals, from more sophisticated policy structuring, for example, through hierarchical and abstract representations, and we discussed before, all the way to closed loop training strategies, so essentially going beyond behavior cloning, all the way to so-called test time intelligence, which is what I want to discuss next. So what you might be familiar with is DeepSeek. And if you are an NVIDIA investor, you're very familiar with DeepSeek because NVIDIA lost about $600 billion of valuation in one day, thanks to the DeepSeek model. Since then, actually, it has recovered nicely. Anyways, so in the past few months, we have witnessed a shift from training time to test time intelligence, where essentially endow an element of real-time planning into these big AI models. NVIDIA has developed its own reasoning engines. One is referred to as a Cosmos Reason 1. There is also a version that is only 1.5 billion parameter model, so it's very good for real-time applications. So why does this matter for AVs? Well, driving is fundamentally a decision-making problem where you have to constantly reason about counterfactual scenarios. What if the pedestrians were to cross the road? What if the other driver were not to yield to me? So language models, explicit reasoning, lets you explore all these if-then branches. So that's why there is such an interest this year from both robotics companies and AV companies are using this new generation of vision language models with explicit reasoning steps. So basically breaking down the problems in multiple steps. Of course, autonomous driving and robotics in general have their own key aspects and challenges, particularly the reasoning. So the breaking down the decision-making process in multiple steps has to be grounded into the physics of the problem. And then the structure of the problem, of course, you have lanes, you have traffic lights, you have rules of the road, and so on and so on and so forth. Everything has to happen quickly. Typically, you want to reply at 10 hertz. And of course, safety is paramount. So we address these challenges in multiple ways. So we have developed specific reasoning models, as they're called, that explicitly take into account the physics of a scene, as I will see in a second. And we look at different types of reasoning from full chain of thought as reasoning traces all the way to compressed meta actions. Compressed meta actions more for real-time control, full chain of thought reasoning traces more for training purposes. So specifically to get the kind of data at scale to train reasoning models for autonomous driving, you have to build a reasoning auto-labeling pipeline. So basically a pipeline whereby you give a video to a model and the model gives you a detailed explanation about why a car did what it did. And then you can use these explanations to then train your own AV stack. But building this auto-labeling pipeline is difficult. It's not as simple as just tagging some boxes and drawing like a human labeler showing where a line is. You really want to break down all this reasoning process. So what we did was to build an auto-labeling pipeline that is essentially a hierarchical system whereby we partition the problem into three key phases. So first, we use a variety of rule-based tools to generate initial meta actions. Think of meta actions as here the vehicle is turning left, or here the vehicle is turning right, and so on and so forth. Next, we bring in large vision language models. Keep in mind that we are doing all of this at training time, so the computer is not really concerned here. This all runs in the cloud. So these models analyze visual frames and identify critical objects, understand the scene dynamics, provide the physical constraints, and so on and so forth. This is crucial to ground visual information, into the spatial physical constraints. And then we use reasoning models such as DeepSeek or others, like the new NVIDIA reasoning or Chuan and so on and so forth, to produce the full chain of thought reasoning traces and then policy rating meta actions that we can finally use to train our AV policy. Let me show you an example that walks through the full chain of thought reasoning process that we use to auto-label all the videos that we have collected with our collection fleet. So the system first analyzes the surrounding environments and identifies the critical objects which may influence decision-making. So for example, here there are 4 vehicles that are identified as the critical ones, including this one that is cutting in front of us. So this is the model, the auto-labeling pipeline that is doing its own reasoning. And then it provides an explanation about what is happening here. So around 3 seconds into the future, a vehicle from the left lane starts to cut into the ego vehicle's lane ahead. This vehicle's movement requires the ego vehicle to decelerate to maintain a safe distance and avoid a potential collision. So it's very different from what you get from ChatGPT, because you see how you can reason temporally and in terms of the physics of this. And then it produces meta actions in terms of what the system. So this is one way of doing abstraction. There are many other ways, but this is one way. Anyway, so once you have these high quality chain of thought data, that is, so this is interesting because all this chain of thought data is produced by using AI. So basically you have an AI system that is training in another AI system. So once you have all this chain of thought data, you can use it to further train your system. And what we saw is is interesting. So here we have 4 different models that were trained with different training recipes. On the x-axis, y-axis is the performance metric. So the baseline achieve a performance metric of 2. It's not, the number is not too important. When we add the meta actions as a training signal, then we dramatically improve the performance. The lower, the better. And then as we expose the model to more and more detailed chain of thought explanations about what a vehicle should be doing, then you get increasingly better performance. Notably, this is only for a curated data set where we consider scenes that are particularly difficult. Think of construction zones or auto distribution behaviors. Of course, in nominal driving, you wouldn't see any difference. Most of the driving is boring, you just go straight. So more complicated chain of thought reasoning online and so on and so forth doesn't really help you with those mundane driving tasks. It only helps in these corner cases, which is the crux of robotics, though. It's very easy to get good performance in 99% of the cases. The hard part is the 1%. All right, any questions here? So all this to say that language pre-training seems to synergize well with the task of driving. And by now, I would say this is pretty old news. So if you come to the Silicon Valley, pretty much all robotics companies out there are productizing vision language models as part of the onboard stack as we speak. Even a number of AV companies are doing that. Besides NVIDIA, there are a number of Chinese companies that are doing the same. The next step is to endow the models with this more explicit reasoning capability online to allow the model to really break down the problem into its steps and further improve decision-making performance. This is still a bit researchy for a number of reasons. Of course, sometimes the reasoning that these models give are completely bonkers. And of course, this is quite slow, so there are still optimizations that need to happen.
Hi, thank you very much for your talk. I was just wondering what you're doing right now. Is it like going towards the large world models that everybody is talking about? Like, you know, you have the DeepMind's Dreamer agents and you have your colleague probably Feifei Li's World Labs, where they're talking about physical AI. Yeah. And would some of the, you know, shortcomings that you talked about, behavior and the uncertainty and the issue of predictability, could be solved with the world problems? That's number one. And the two, the importance of training data. So obviously your models require some baseline training data, and probably that can't be kind of applied to a European city, what it can be applied to San Francisco. So the importance of training data for this transferability of these technologies. Thank you.
Yeah, two great questions. So I only talked about video generation models, or more broadly world models, in the context of simulation. And that's probably the first key obvious use case: simulation and synthetic data generation. Well, of course, those models can also be applied as part of the onboard stack. So something that we as NVIDIA, we're doing is, for example, to distill down the features from video generation models from Cosmos specifically into the AV stack to improve its spatial reasoning. So that's definitely a direction moving forward. I would say that the use of world models in robotics is lagging a bit behind the use of language pre-trained models. One of the reasons is that video generation models or world models are more recent. By now, vision language models have been around for 3-4 years. Video generation models, world models, have become really popular since last year. So people are still trying to understand exactly how to best use these models as part of a physical system. But definitely, there is going to be a sort of unification between these two types of foundation models: video generation model, world models on the one hand, and large language models. And yeah, people are working on it, including myself. Regarding the quality of training data, so I think there are two different aspects. So the first aspect is that now you're shifting the burden on the performance on the quality of the data that you use to train the system. So what if you have bad apples in your training data? Then you're going to get bad behaviors at the output. So we're going to actually address this aspect later in the presentation. In the case of transferability, well, this is actually one of the motivations for using these kind of large pre-trained models. So the hope, and actually also the evidence, is that you're able to acquire generalist knowledge that hopefully allow you to transfer more gracefully across different geographical regions. That said, geographical expansion is still a big problem, especially for high levels of autonomy such as L4. For example, Waymo opened its first robotaxi services in Phoenix in 2020 or 2021. And then it opened a couple of more in San Francisco and LA a couple of years ago, well, LA this year. And then it expanded to 2-3 more cities. But as you see, actually the deployment in new cities is relatively slow for a number of reasons. Of course, there's also safety, regulatory, and so on and so forth. But one of it is actually expanding to other geographical reasons is challenging. But we'll come back to the question of data quality shortly. Now is a question for you. So in the program, you had as a time allocation until 12:30. How much time do I have?
Let's go ahead.
Now, I don't know if people are bored or...
The questions from the web.
Because the question time is between 12:30 and 1. Exactly. So I don't know if you want to stick with that program, which is basically, in principle, I should be talking for another hour, or and then I will be completely melted down, or...
Let's take a vote.
So so now the topic that I would like to address in some depth, which is very important, is the one of safety. And there are different aspects related. There is no silver bullet to actually inject safety into a system. So there are 3 main aspects that I wanted to tackle. So one is whether we can use a simulation for validation. And the second one is how do we reason about data quality? For example, how we remove unsafe behaviors from the training data. And the third one is how we use foundation models to make a system safer through the lens of semantic runtime monitors. Any preferences? I can do all 3. Okay, so we'll quickly mention broadly what we're doing on the safety side, and then we'll talk a bit about data runtime monitoring and only briefly mention simulation for validation. And then if we want to talk about it, we can. So as I mentioned, rightly so, there are a lot of concerns about fielding foundation models in a driving stack. All of you are familiar, for example, with hallucinations from a ChatGPT. You don't want your model to hallucinate as the model is driving. And my point is that while these are all valid concerns, it's important to recognize that foundation models are not black magic. They are fundamentally data-driven models, albeit large ones, for which the automotive community has a lot of experience in terms of fielding them in a safety critical context. Now, there is no silver bullet in order to ensure and assure the safety of an AV system. And I like to think about imbuing safety as a process that really spans the full life of the product. And in particular, I like to think of safety as essentially injecting guardrails into 3 different phases. At design time, so as you're designing the system, we talk about the design time guardrails. So these are steps we take in the design and training of a foundation model-based stacks in order to make sure that they produce safe behaviors. For example, curating a data set by removing unsafe behaviors, or devising architectures with enough diversity and redundancy so that you can achieve your target KPIs. For example, what I've shown so far are essentially end-to-end architectures that use the foundation models. But in reality, the way that NVIDIA and other companies think about it is to have these powerful AI models that run in parallel with more classical and fully validated driving models that use more classical techniques, maybe rule-based planning and so on and so forth, and then combining the two through arbitration mechanisms so that most of the driving is typically done by the powerful AI model, but there is another model that keeps the AI model in check through cross-checking of the signals so that in case the AI goes crazy, we can gracefully transition to the more classical stack or a contingency plan. So these are design time guardrails. Then we have runtime guardrails that acts as another layer of assurance. Think of these guardrails, for example, as runtime monitors that constantly monitor the health of the system, for example, the input level, to ensure that your system is operating on inputs that are not too different from the one seen at the training time. or at the output to measure that there is actually consistency in the outputs that are generated, and so more, and so forth. And then verification and validation guardrails. So basically all the techniques, including simulation, that are used to ensure that your model meets stringent safety KPIs. Of course, safety is not a linear process. And while the material presented in the previous slide was presented in a sequential fashion, building a safety product is really an iterative product where you constantly learn from the real world, and based on that, you retune all your runtime monitors, you extend the operational design domains within which you run your AI, and so on and so forth. So this leads to the notion of a safety data flywheel. So certainly several of our research on the topic of AI safety has now been integrated into the NVIDIA Halos safety program. So as announced by the CEO of NVIDIA, Jensen Huang, at the last GTC, Halos is a comprehensive safety system for physical AI, and Ricardo and I are fortunate to serve as its tech lead. So in the rest of the talk, as I mentioned, I wanted to focus on 3 topics. Maybe I'll focus only on 2 in the interest of time. So the first 2 related on how we build a safe product in terms of can we use simulation for validation, and how do we reason about the data flywheel. And the last one in terms of runtime monitoring. For simulation for validation, let me just quickly give you the idea, and then in case we can come back to it later. So typically the way the simulation is used is for testing and for potentially training. And in testing and training, typically you are only interested in a directional signal. So you have a policy A, decision-making policy A, you have decision-making policy B. The question that you have is typically, is decision-making policy B better than decision-making policy A? The specific numbers that you get out of the simulator are not too important. For validation, you really care about the absolute performance metrics that are derived from the simulation environment. For example, what is the mean time between failure in a given operational design domain? So the question is, can you trust simulation when what you care about are these absolute performance measurements? So that's tricky, because how do you build trust in those absolute performance measurements? In principle, you will need to validate your simulator with the real world data. So that's difficult. But second of all, 2 policies might actually depend on different aspects of a simulator. So once you have a new policy, the new policy might latch on different aspects of the input, which means that you may need to revalidate the simulator to make sure that actually you can still validate the new policy. So that defeats the purpose of using the simulation if every time you have to use real world data to revalidate your simulator. So more programmatically, some work we've been doing that is getting quite a bit of traction is how we can actually pair simulation and the real world testing in a way that allows you to carry out the validation in a much more data efficient way. And for those of you that are familiar with statistics, basically we use the framework of control variates. And essentially we use the simulator engine as a control variate for the data that is collected from the road. And we show that actually we can achieve dramatic improvements in terms of how much less real world data it is needed to achieve the estimation of a given performance metric for a given level of confidence. But as I said, we skip all of that. We can talk more about it later. And instead, we'll talk a little bit about data. So essentially, simulation allows you to identify possible performance gaps, for example, through testing. Considering this time manipulation, just to change a little bit topic and look at robotics instead of autonomous vehicles. So these are the type of things that can still happen with modern AI technologies. For example, a robotic manipulator might lack the precision to tie a cleat, or may choose a fragile pushing strategy to tack a box with an uncertain mass under a shelf, or might ignore other objects. So for example, this manipulator is picking a book and is dropping the other book. And we'll see that this is due to some spurious correlations that are learned through behavior cloning. So having identified such gaps, the next natural question is, how can we systematically identify the root causes of these problems and improve end-to-end performance? So for policy trained end-to-end, you don't really have a control logic that you can simply modify. Rather, reasoning about AI performance requires explicitly relating test time behaviors to the quality and composition of training data. For example, low precision in carrying out a specific task might be due to mixed skill levels of demonstration. So some humans actually might be better than others in terms of demonstrating skills that then the AI can learn to learn its decision-making policy, or by some of the diverse strategy demonstration being more fragile, or because the model might pick up spurious correlations. So for example, here there is a setting whereby in some cases we have only one book into the shelf, in another setting we have 2 books, but the background is different. And so actually the robot learns what to do, not based on how many books you have on the shelf, but based on the background of the wall, which makes no sense, right? So these are referred to as spurious correlations. So once you see such poor behavior, how can you identify in your data what are the data points that are the culprits for such poor behavior? So concretely, suppose that we train a policy via behavior cloning. So essentially what we do is we collect expert demonstrations, and then we train the policy to mimic what a human has demonstrated. And suppose that they evaluate a closed loop performance. Qualitatively, we want to understand what training demos drove a given test time behavior, but how do we formalize this goal? So our key insight is to develop methods to counterfactually reason about the inclusion or exclusion of a specific data point in the data lakes. That is, our goal is to predict counterfactual, like how does the predicted return change if we were to include or exclude a given data point, a process that we refer to as data attribution. To do so, we turn to the theory of influence function, which is a foundational tool from robust statistics that traces its origins back to the 1970s, and it formed a foundation of interpretability research in machine learning since the seminal paper of Percy Liang, who is a colleague of mine at Stanford, in 2017. So influence function effectively compute a first-order sensitivity around reweighting a training sample. Specifically, consider adding an infinitesimal weight epsilon on the loss of some training demonstration. So this is your standard behavioral cloning objective. Think of, we want to match as close as possible what a human would do in a given situation. And then we upweight one particular demonstration and see how that upweight would transfer in a change in a closed loop performance. Specifically, we want to compute the influence of the sample on the policy performance. This is the change in expected return J with respect to infinitesimally upweighting important weight epsilon. So that's the derivative that we want to compute. So in practice, compute this performance function is not easy. For one, data attribution tools typically can only attribute an individual prediction back to a specific training sample. And here, instead, we are interested in the outcome of a sequential stream of decisions. And second of all, of course, we don't really know the environment dynamics. So we don't really have a closed form equations that link the training data to closed loop performance. So our insight is to apply policy gradient tricks. So if you're familiar with the policy gradient algorithm, to decompose the performance influence functions into a tractable sum of the influence of training data on the action log likelihood of the policy, which we can easily compute by using existing techniques from recent work from MIT called TRAC. So the main point here is that these derivative can be evaluated empirically as an empirical average with respect to some policy rollouts of mathematical objects that we can compute relatively easily with standard tools. And again, if you're familiar with policy gradient algorithms, the math is very similar to policy gradient pipelines. So then what we can do with this tool is to learn a policy, perform some policy rollouts, and then use this formula that had faith in me that is accurate, and then use it to score the different demonstrations that were collected and stored into the data set. And the score basically tells you to what extent a given demonstration affect closed loop performance, either in the direction of goodness or in the direction of badness. And then based on that, then you can decide whether to remove some of your data or add new data, for example, to reinforce a given good behavior. And actually, we show that with this pipeline, we can fairly seamlessly prune low-quality samples, identify more robust strategies, and root out spurious correlations. So these are all the failure modes that we saw before. We took a state-of-the-art diffusion policy from the literature, and we show that this pipeline, we can dramatically improve performance. So this pipeline is referred to as Cupid, curating data your robot loves. So I was very proud of this acronym. So I congratulated my students. Then I found out that actually this acronym was generated by ChatGPT. So the students confessed. Still, I think it's a nice acronym. Anyway, so this just to show is one of probably the first tools that allow you to reason in a principled way in terms of how data is linked to closed loop performance and how to use that link in order to inform model retraining. All right, so last topic. So something that has been somewhat overlooked in the literature is how foundation models indeed provide opportunities to improve the performance of the safety of an autonomous vehicle. And here I want to look at this opportunity specifically through the lens of runtime monitors. So to make the situation, discussion concrete, let me show you an example. So this is a video from a Tesla display. As you see, it doesn't make any sense. So there are some traffic lights that are spawned by a truck. Well, so that's the image at the beginning. Well, now you see that it is a truck with traffic lights, and then the Tesla autopilot is interpreting those traffic lights as real traffic lights. Or here is another example of a scenario that is causing trouble. So here we have a stop sign that is printed on a billboard. And then there is this angry Tesla customer that complains that every time his vehicle or her vehicle goes through this billboard, the vehicle slams on the brakes. These events are referred to as ghost brakes. And that's definitely an annoyance, but also a safety hazard because you can be rear-ended. So I refer to these anomalies as semantic anomalies. So these are anomalies due to a very unusual combination of in-distribution events. What I mean by that is that here you can't really say that, for example, the detector has been malfunctioning. It has detected the stop sign. But the model lacked enough semantic and contextual understanding to understand that this is actually not a cause for trouble. So the point here is that while it might be very difficult for a system designer to really think about all of these different cases, all that the vehicle needs is a little bit more of semantic understanding of a scene to negotiate the scene well. And so for this, again, we train to the merges capabilities of a vision language models, similar, but in a different way with respect to how I mentioned it before. So specifically, we are considering the following experiment. We recreated the scenario of the traffic lights on a truck in a simulator, in this case, a Carla. And then we explored the idea of using a general purpose open vocabulary detector to parse the scene, which finds, among other things, that the scene contains a truck that is carrying a traffic light. And then we use this information with an input prompt template, which describes essentially what the job of a runtime monitor is. We give this prompt to a large language model, think of it as a ChatGPT, and that's the output that we get. So we see that for some of the elements of the scene, those are classified as completely normal, like for example, a tree, no cause for alarm. But for the traffic light, look at the answer of the model. So it says that this is an anomaly, but interestingly, it also provides explanations for why this is an anomaly. So this is a different use case with respect to the one before. So here we're using a large language model, not as part of the primary algorithmic pipeline, but more as a parallel monitor. that is checking what's happening and potentially triggering an alarm. Now, of course, one of your concerns might be that you can't really run a ChatGPT online, which is true. So then we worked on how we can get the same benefits of this pipeline, but in a way that is real-time capable. And here our insight is that to basically disentangle the task of anomaly detection from the task of contingency planning. Think about how you typically drive. So typically when you drive, you don't think about driving. But I would argue you have a sort of anomaly detector in your mind that is constantly checking if there is something that is potentially dangerous. And checking if something is dangerous is relatively quick, it's binary. Something either is dangerous or not dangerous, roughly speaking. Then if there is something dangerous, what you do, what you should do, is to slow down, to buy yourself a little bit of time to think through the scene and then decide what to do. So that's essentially the idea that we implemented as a refinement of the previous idea, whereby we use large language models embeddings to do anomaly detection. As I will show in the next slide, this is something that we can do quickly. And then once an anomaly is detected, then we call a full-blown autoregressive model to generate the full contingency plan. And everything is orchestrated through a model predictive control pipeline that also models the delays that you incur by querying a large language model, so that as an emergent property, you have that the vehicle would slow down the dynamics to buy yourself a bit of time. So specifically, the idea is to use a large language model encoder to compute embeddings from the robot prior experience, nominal experiences. So all these embeddings are stored into a vector database. Then for new observations that come in online, you compute the embeddings for that scene, which only requires a forward pass of a transformer, so that can go very fast. And then you compare your new embeddings with embeddings of nominal experiences, and you form a sort of a distance function in that space. And then if the distance is too high for a threshold that is properly calibrated, then you say that there is something anomalous. In that case, you call a full autoregressive model to generate, to think about the contingency plan, or otherwise you keep going. So let me show how this works. So on the left, we have the pipeline without the runtime monitor. The vehicle is driving around. It sees the stop and the stop sign. It's weird, but doesn't have enough semantic understanding that that stop sign is not a real stop sign, so it stops. So that's that. Instead, with a runtime monitor, we use the large language model embeddings. They still have some level of semantic reasoning because they are LLM embeddings. We detect an anomaly, but then once you saw that the vehicle slowed down a little bit, that's when it was querying the full-blown large language model to generate a contingency plan, and then it decides that it can go. So more in detail, so here we detect the anomaly, and we can do this extremely quickly, so in the order of a few milliseconds, which is crucial. A runtime monitors is essentially an additional algorithmic pipeline that you have to ensure safety. And you want for the monitor to be as lightweight as possible. And once this anomaly is detected, then we query, in this case, the GPT 3.5 to reason about the anomaly. So we show that at least for our specific implementation, we can achieve a 97% true positive rate and overall accuracy of 77%. The false positive rate is a bit high, is about 54%, but at least you err on the side of caution. Of course, if you use larger models, you get better accuracy, but then you have a worse latency. But there are many other things that can be done here. And this is, again, another idea that is getting quite a bit of momentum in the community. Some of the things that we are working on and other people are working on is, for example, how do you reason about the multi-frame observations as opposed to just the most recent frame? How do you reason about uncertainty? How do you fine-tune the model to AV data? So here is a minor miracle that, at least for this paper, we were using GPT 3.5 out of the box with no AV fine-tuning. We have been applying this monitoring pipeline to many other domains, including quadrupeds moving in construction zones. You can see the quadrupeds can understand that here there is yellow tape, so it can go through. These are all emerging behaviors, not scripted. there is a person that is carrying an object, so it should stay away. So it's more in maritime applications and so on and so forth. Anyway, so let me wrap it up here. So the point of this talk was to show you how foundation models provide key opportunities to probably they are right now the best tool we have in the community to boost the generalization capabilities of robotic systems toward a North Star of building generalist policies that allow a robot to really work in the wild. In the case of autonomous vehicles, work in any sort of operational design domain, in the context of a robotic manipulator, manipulate any type of object. Importantly, even though, especially in the academic community, foundation models are primarily discussed in the context of how to improve online performance, so basically the software that goes into the robot system. Foundation models provide equally important gains also in terms of offline development processes, how you improve simulation, how you improve labeling. Something that we haven't shown, for example, is how do you measure performance? Performance is not as easy to measure as you might think. Like, for example, certainly you don't want to collide with an autonomous car, but what does it mean to drive well? Well, you can use actually AI tools to score the type of performance characteristics. Then we looked at the use of foundation models in 3 different settings. In the setting of offline processes, particularly simulation, we show in particular how foundation models can help with the scenario generation and can help with generalizing new scenes through video generation models. Then we looked at how to use foundation models as part of the onboard stack. And I argued and showed evidence about how language pre-training synergizes well with the task of driving, and how, going one step further, explicitly using reasoning traces that modern language pre-trained models produce can further improve performance. And finally, we discussed how safety, of course, is a key consideration for the deployment of these powerful AI techniques. There are a number of different tools to reason about the safety topic, but at the same time, foundation models provide opportunities for making the V-stack even safer, for example, by enabling semantic runtime monitors. So with that, I'd like to thank all my collaborators, both from Stanford, NVIDIA, and yeah, happy to answer any questions.
Now we open the floor to questions. For more questions, we give priority to those in the room, and then we have some questions already booked on the web that we will read out after the local questions. Thank you.
Thank you. Question about the chain of thought. Is there any plan or any usage by NHTSA to be used as an evidence for accidents involving AV?
Yeah, so forensic use of chain of thought or more broadly vision language models. I don't know if there are plans from NVIDIA. I do know that actually we have a couple of papers in terms of how we can use foundation models for blame assignment. And I was also doing some of this research in collaboration with some of this discussion in collaboration with an insurance company, Swiss Re. So I think the forensic use of foundation models can be a very interesting one. I don't know if NHTSA is adopting this tool yet. That I don't know. I don't know if you know, Ricardo.
First of all, thank you for this presentation. That was really, really stimulating.
Thank you.
I was wondering if you have a notion of risk level. So there are behaviors which are more risky and others that are less risky. For example, if you have a person walking in the road, you should be more attentive than when you have a stop sign. Are you taking this into account? Do you have any kind of hierarchy modeling the different levels of risk, or everything is so far is flat and you take into account everything in the same way? Because I think also the reaction could be different in timing, etc.
Yeah, yes and no, in the sense that for the end-to-end model specifically, at least in the simplest instantiation, is a fully data-driven model. So all these risk levels are implicitly learned from data. And that's the point, that having a system designer that think about all possible risk levels for all possible situations in all geographical regions is a very daunting task. At the same time, these data-driven models also have limitations. So as I mentioned before, what people do is typically to augment these end-to-end fully data-driven stacks with more classical stacks that, for example, use more model-based design techniques for decision-making. So you have explicit formulation of constraints, and there the notion of risk levels is integrated. Then a completely different topic is how you do carry out, and here we have one of the world experts, how we carry out a risk analysis in order to understand the safety KPIs against which you want to assess your product. And so that basically has to reason about the frequency of an event, the severity of an event, and the controllability of that event. So basically, if the AV could do something, of course, if an asteroid is aiming at you, there is nothing you can do, right? And then based on that risk type of analysis, you derive KPIs and requirements with respect to which you want to spec your product. But this is sort of complementary to what you do in the online stack. So that's why I said yes or no. In some part of the stacks, you don't do it, but for a reason, because that, limits in a way the capability of the model, because it injects all these prior assumptions that sometimes may not be fulfilled. But some level of it has to be present, right? At least for diversity. And so that's what people typically do as well.
Thank you.
Yeah.
Any other question? Yes. Part two.
So thank you for the presentation. I have a question related more to the process than to the technical setup. The anomaly detection, so you try to move the anomaly detection out of the automotive case, and we saw nautical drones and whatever. How difficult was to find out the anomaly cases that you usually easily find in the automotive case, because they are on Twitter, they are on the web in general, and how do you perform the first part of the experiment where you build the database of the anomaly? Because if I have to think about, for example, try to apply this case to aviation or military field, how I can get the first part, so the anomaly database.
Yeah, that's important. So we don't get an anomaly database. And that's
Okay.
a key point. Because anomalies are something that you can't really foresee at the design stage.
So the anomaly was when you pass the threshold only.
That's right, yeah.
Okay.
So you build actually a database of nominal experiences.
Okay, and so you get anomaly automatically.
Okay. That's the motivation actually about, I mean, at the end of the day, why people are excited about using foundation models is that reasoning about auto-distribution events, so stuff that you've never seen, never thought of, you can't because you have never thought of. So the idea is that these models have been exposed to internet scale pre-training. At least notionally, they have seen everything, including the stuff that you haven't thought of. So they provide a handle to think about what to do in that case.
Okay.
But you need to understand when to give a power to the foundation model to think about the thing that you have never thought of. In terms of tuning these thresholds, you can't use auto distribution data because by definition you don't have it. So that's why we build the mirror version of it, which is the database of nominal experiences.
Okay.
That said, then at some point you have to test if this stuff works, right? And so that's tricky. Like, for example, a lot of the work in the paper that I mentioned that was using the Carla simulator, we spent most of the time was actually in handcrafting anomalous scenarios that made sense. Because, yeah, you don't have that many that... So doing research, actually for research purposes, that's tricky because you have to generate them somehow to show that your method works.
And just to ask, do you use, I didn't read the paper, obviously, because I just discovered it actually.
Yeah.
But do you only try those events that you find out in the internet, like the funniest one, for example, the stop or the traffic light, or do you craft? Okay.
No, no. As I said, I mean, those were just qualitative examples to make the point. But of course, those are just qualitative examples, right? Now, in the paper, we have a full, rigorous evaluation with respect to many more cases where we derive statistics and so on.
Thank you.
Oops.
Just a super quick question. Even assuming that using computed test time is going to work, what about the energy consumption? I mean, I cannot imagine cars that are using, you know, a lot of compute at test time. I mean, we need a nuclear power plant just for the cars in Turing, right? So, is there a role for edge computing for, say, circuits that are kind of autonomous, say, not centralized or something like that? Because otherwise, I don't see how to match the numbers.
Yeah. So first of all, chain of thought reasoning traces can be used, for example, at training time to, you know, better imbue these kind of capabilities in the model. But at the inference time, you don't need to necessarily generate a full chain of thought reasoning trace. For example, what you can generate is what I refer to as compressed meta actions. That said, NVIDIA has different chips. So the one that is currently in production is called Orin. And for that specifically, using a full test time compute is excessive, will be very, very difficult. Maybe you could get one or two meta actions, but that wouldn't move the needle too much relative to what we can do today. But the next generation version, Thor, is designed specifically for heavy-duty transformer-based workloads, including reasoning models. Of course, we're not going to generate like a reasoning traces for several seconds in the future. That probably wouldn't be useful anyways. But some level of it, it will be possible with chips that will be becoming available soon. That said, what I showed is only one example of test time intelligence, but there are many other examples of test time intelligence, as I was also mentioning before. Right now, pretty much everybody does the most naive thing, so whereby the decision is represented as just an open loop trajectory. But for those with a control theoretical background, they know that that is a very simplistic way of representing a decision. You can represent, you can, for example, produce multiple trajectories at the same time, or a value function with uncertainty, and then you can do test time search with respect to the value function. That's still test time intelligence. It just doesn't use reasoning traces. Or another planning framework that is gaining some popularity, but for now is most academic, is the so-called planning then evaluate framework. So this is something that actually uses more world models related to the previous question, whereby you essentially use these powerful world model features to forecast different scenarios. And then you use a vision language model to pick the scenario that you would prefer. And then you do search within that scenario. So all of this to say that there are many variations of test time search. I only show one example. And that's typically in control. You know, there is always the pendulum between how much compute you do offline and how much you do online. And, you know, the community always goes back and forth, like with MPC. First was all, online, then offline, then it's coming back online. It's the same thing here.
Hi, thanks for the insightful presentations. I was wondering to ask for the online policy and introduce latency. I find intriguing storing embeddings into a database, but I was wondering how that could scale. I mean, if you could continue adding more data. And also, I was wondering to ask whether you think it could be useful to train like these still small yet fast models, like experts for like input modality, for example, either or RGBs or for output, and then just use a small and fast orchestrator to understand which one to use or which experts to use if more of them.
Yeah, so the first question was about this data set for the nominal experiences. Yeah, that's a great question. So in the paper I show, we use about 1,200 embeddings. which is not enough actually to cover all possible nominal experiences. Actually, the paper we're working on, and if you're interested, send me an email, and in 2 months I will share with you, is actually how we can, once you build this very large data set, how we can do pruning in a data set so that it's something that you can store in a vehicle. That's an excellent question, but there are ways to actually distill down that information to something that is usable in real time. And then the second question was?
The second question was
the distillation.
Yeah, I mean, I understand training a huge reasoning model, but then what about using distilled versions to act like real-time scenario?
I mean, first of all, some of the models we've been discussing already distilled down version of larger. So essentially, to just give a rule of thumb, what you can conceivably run on edge compute runs between, I mean, don't quote me, but say 500 million model parameter to maybe 2, 3, maybe. Of course, it depends on many other things, how much information you condition your model with, how much you generated the output, and so on and so forth. But rule of thumb between 500 million and 5 billion. So some of the models I presented are already distilled down versions of models that maybe 70 billions and more. So what you're pointing to is something that actually is a little bit more similar to what I presented with Agent Driver. So essentially, you have models that are sort of called on demand by a sort of an orchestrator. That's a possible architecture. I think for autonomous driving might be tricky due to latency requirements, determinism in the computational path, and so on and so forth. But from other applications that might be either embodied or disembodied, could be perfectly fine. The good thing is that that specific architecture is very easy to set up. Way easier than a full end-to-end stack. And also, as a designer, I mean, as a roboticist, if you have your own company, it also allows for some level of modularity. Maybe you can get some very nice models for segmentation from SAM, like from Meta, and then you develop all your own, and then you have a little ChatGPT that coordinated the entire stuff, and boom, you have a very nice robot that can do stuff. For autonomous vehicles, it's a bit harder.
Thank you.
So, but that said, I mean, one of the reasons why I say architecting is one of my favorite topics is because there is a huge space, and it's still very open in terms of what best architecture is best for what. And there is no like monolithic architecture that is best for what. So, robotics manipulator, humanoids, autonomous vehicles, they're similar, but they're also a bit different. So there's this space for exploration.
So maybe we take the questions from the web. You want to read them out?
Yeah, I'll do. You have certainly met Bill Clancy at NASA, and okay.
Okay, so working on Mars. His father has been a synergy human-human agent human relation with the ancestral connection. I mean, I don't know Bill Clancy, and I don't know his work specifically, but of course, the work we've been doing on behavioral modeling and the behavioral prediction is based on a very large body of literature on modeling humans in their decision-making process. There are many different ways of doing so. There are some models that are more grounded into inductive biases, like game theoretical models. Those are maybe, in the context of automotive, more useful for automated racing, where there is a clear notion of competition and game. So I don't know exactly what is the relation to the work of Bill, but definitely, of course, the work is not in a vacuum. It is more and more equipped with intelligence. Okay, so I use intelligence just because everybody uses the word intelligence. Of course, there's always a slippery slope to define exactly what intelligence is and what we're doing with intelligence. And our previous question is not yet. In the real world, all occurs interactively. Yeah, so there are two aspects. So of course, in the context of autonomous driving, communication as part of the interaction is implicit. So the way that you communicate it to other people on the road is through the motion of your own vehicle. So for example, if you are nudging, I mean, that's communication. So you're communicating, I mean, apart, of course, from the lights that you have in your car. But if you're nudging, that is communication for other people on the road that you want to execute a lane change. But typically communication is only implicit. There are some companies, though, that have been exploring the possibility of using explicit communication. Like, for example, some autonomous shuttle companies, they literally had some displays telling people outside that, look, I'm about to cross the intersection and so on and so forth. But this is not so popular. Then there is the third aspect of communication that it was quite popular a few years ago, not so much anymore, which is communication not so much with other people on the road, but with the infrastructure. Like, of course, if you had intersections that are instrumented with cameras that allow you to get additional visibility into occluded areas, that would dramatically simplify the task. But none of the company I know of is looking at vehicle-to-infrastructure communication, which seems crazy because essentially we're solving the hardest problem first. But the reason is that if you expose your decision-making process to outside the communication, then first of all, you're introducing latency into the system. But of course, you're also then introducing a significant cybersecurity challenge because right now, the decision-making policy is completely shielded from the external world. So unless you temper the sensors, there is no way you can hijack, almost no way you can hijack an autonomous car. But otherwise, if your car starts communicating what you want to do, it's very easy for other actors to potentially spoof the communication system. And at the same time, you can't put a beacon on every pedestrian, so you would only outsolve the problem. In terms of interaction, so, well, that's, for example, one of the reasons why we've been looking at the potential of using reasoning traces. Those actually explore if-then branches that take into account possible interactions. And interactive decision-making, at least in end-to-end models, is implicitly encoded in the policy that you learn from expert data. More classically, the way that interactions was modeled was through developing behavior prediction models and then condition action generation with respect to different predictions. But this has been largely replaced these days by end-to-end stack, whereby interaction reasoning is only implicitly acquired as a skill as part of the neural network training. So long answer to say that communication, of course, and interaction is crucial. I mean, it's probably one of the distinctive features of autonomous driving with respect to robotics. Robotics is much harder because you have to reason about tactile sensing and the friction and so on and so forth. Physics is complicated. Autonomous driving is much harder, on the other hand, because it has to reason about interaction. So more or less this is what I can say about this question. Well, so I mean, here, maybe I can just echo what the CEO of NVIDIA says, that physical AI is actually the next step of agentic AI. So it's agentic AI, but with a physical embodiment. So yes, of course, physical AI is agentic AI in the sense that there is an AI that is making decisions. Again, these are also levels, right? I mean, even AI models we had 2-3 years ago, we're already making decisions for autonomous cars. But anyway, so physical AI is definitely agentic AI. The main difference is that you have a physical embodiment. So that changes things quite substantially for all the reasons that I discussed today.
I think I just want your outlook on the open versus closed models, because I saw in your stack, I saw Mistral, Llama, and Stable Diffusion. So you've probably used the open source models much more. So what's your take on proprietary models? Would your performance improve, or how do you see the open versus closed models in this space? Thank you.
So for some things, like closed models are still doing a bit better. That said, maybe because I also have an academic hat, I'll be a proponent of an open model. And I think the gap is also shrinking quite a bit. And NVIDIA specifically is pushing for open models. Like, for example, Cosmos is on a Hugging phase and such. So I think in the long run, probably we'll be able to use open models. I mean, of course, there are considerations about how you can use open models as part of a commercial product and so on and so forth. But at least in terms of research, we'll be able to use open models as well as closed models. And again, NVIDIA has a plethora of open models right now currently available and of very high quality.
Hi, thanks for the presentation. Just a very quick question. What do you think about the benchmarking for the LLMs? So we got a chance to see a lot of application in terms of autonomous vehicles and the scenario description or interaction between large language model and other kind of robots. But what do you think about the LLMs benchmarking, and what could be the impact of wrong benchmarking on this kind of application?
LLM benchmarking in terms of typical LLM tasks, or in the context of physical AI?
Oh, in the context of physical AI.
Yeah, so I mean, if you go to any robotics conference, or you always find a panel that discusses about the lack of benchmarks in robotics, which make the field relatively non-scientific. I typically joke that, you have different type of proofs. You have direct proof, proof by contradiction, and then you have proof by video. So if you go these days to robotics conferences, a lot of the times you have, oh, look at my video, it works. So that clearly means that my model is better. And one of the reasons is that there are not a lot of benchmarks out there. One of the reasons that is tough, because of course different robots have different embodiments, so unifying those benchmarks in a way that is meaningful is tricky. For robotics, for autonomous vehicles, there are a bit more benchmarks available. Waymo, for example, has set up several benchmarks for different tasks, from behavior prediction to end-to-end driving, LLM-based end-to-end driving, and so on and so forth. There is the new scenes type of benchmark, and there are many others. NVIDIA is actually taking this challenge and is in the process of releasing a very large data set for physical AI the community can use for benchmarking, that is going to span both robotics and very soon AV. Actually, there is already something for AV, but it's still minimal. There will be much broader release in the next 3 months or so. And you're right. I mean, this is necessary, especially as the field is becoming increasingly more empirical. You need data really to show whether you are moving in the right direction or not. And especially for robotics, this is lacking a little bit. But I think the community is moving in that direction quite quickly.
Thank you.
Thank you very much. I think we can come to a close. Temperature has gone to unbearable levels. So thank you very much. A big warm applause to Professor Pavone. A couple of administrative. Professor Pavone and Mr. Mariani from NVIDIA will be with us again tonight at 5:30 here in OGR at the other extreme in the Mind Machine program, which is much more divulgative and less technical. So if any of you are interested in such a different view on similar subjects, please join us at 5:30. I would also like to remind you that these cycles of seminars will continue in September with 2 new seminars, one from Professor Ben Porad from the IMT Center for Advanced Studies in Lucca, and another one from Professor Zecchina, who we have the honor to have with us today from Bocconi University. So thank you very much again for being with us. I hope this was informative and interesting. Definitely it was somehow a little bit technical, so for the most technical savvy of you, thank you again. Let us have your feedbacks and see you soon on this program. Thank you very much again. Bye.